So we've made it to the last section in chapter 2, which is proof by induction. And I think for a lot of math majors, proof by induction is the most sort of baffling when you first see it. It's the most mysterious of the proof techniques. You sort of have to buy into it to really believe that this is a valid proof technique. It takes some real deep thinking to try and understand how this works. So before I really define what proof by induction means, I wanted to sort of give you an analogy for how this works. So we can think about a proof by induction as a method of knocking over a big long line of dominoes, right? So if you want to make sure that your dominoes actually will all knock over, let's say you have, here's your stack of dominoes. Can you see this in the video? Okay, yeah. You got a stack of dominoes here, and let's just assume that there's infinitely many, because why not? What would need to happen in order for you to be sure that all of your dominoes got knocked over, all infinitely many of them? So two things have to happen. First of all, you're going to have to knock over that first domino yourself. You must knock over the first domino sort of manually yourself. And then what else needs to be true? Well, we have to make sure that the dominoes are close enough together that the first one will actually knock over the second one, that the second one will knock over the third one, that the third one will knock over the fourth one, etc. You can't have any gaps here. If you had like a gap in between and this domino fell over without actually reaching the next one in line, then eventually this would stop at a certain point and you wouldn't knock over all the dominoes. So for every domino you have, let's say the kth domino in line must be able to reach and knock over the next one in line. So we can say the k plus first domino in line. Right? If at any point you had domino k and it doesn't quite reach domino k plus 1, then there's no way that you're going to have all your dominoes knocked down. So this is sort of the idea behind a proof by induction. We show that the first case of a particular statement is true, and then we show that for a particular case k, if k is true, then that implies that k plus 1 will also be true. If we can show those two things, then we'll know that it's true for all n. Right, so let's go ahead and try and make that a little more explicit here. So the principle of mathematical induction states that for every natural number n, if p of n is some kind of an open sentence, right, some sort of a statement, that if p of 1 is true, so if the statement is true when n is equal to 1, and if for every natural number k, we have that if p of k is true, then p of k plus 1 is true. So this is saying the conditional statement p of k implies p of k plus 1 is true. Let me just say, that is, if p of k is true, then p of k plus 1 is true. If these two statements are both satisfied, then we can conclude that for all natural numbers n, p of n is going to be true. All right, let's try to make sense of this here. So essentially what we need to do if we want to try and prove that a statement p of n is true for every natural number n, we first need to show that it's true for the base case. In other words, explain why the statement p of 1 is true. This is usually the easy case. You're just replacing n with 1 and explaining why that equation is correct. The inductive step, this is where things get hard, right? So for the inductive step, we say, let k be some number greater than or equal to 1, and we assume that the statement p of k is true. Okay, why are we assuming this? Well, essentially, this is the statement that we're trying to prove right here, and we're trying to prove it directly. So we assume the hypothesis, assume that p of k is true, and then we prove the conclusion, prove that p of k plus 1 is true. So then show P of k plus 1 is also true. Having done these two steps, we can conclude by the principle of mathematical induction, just shortening PMI to principle of mathematical induction, that P of n is true for all natural numbers n. Okay, again, this probably seems pretty abstract and a lot of the language looks a little weird, so we're going to do an example just to try to wrap our heads around what's going on here. Okay, now, we want to prove that for every natural number n, the sum of the first n odd integers, or first n odd natural numbers, is equal to n squared. All right, let me just try and convince you that this is true for some small cases of n. So when n is equal to 1, this equation is actually much shorter than what I've written here, because we really just want the sum of the first n odd natural numbers on the left-hand side. So when n is equal to 1, that's just the first one odd natural number. So the left-hand side here would just be 1. Okay, now we're claiming that that's going to be equal to n squared. Okay, well n is 1, so 1 is equal to 1 squared. Yep, that's true. That's going to be useful down here because that's the base case. Already done. All right, for n equals 2, we're saying the sum of the first two odd natural numbers, that would be 1 plus 3, is equal to n squared, so 2 squared. Yep, oh, 2 squared, sorry. I don't know why I put a 4 there. 2 squared. 1 plus 3 is equal to 2 squared, that's correct. For the n equals 3 case, we want to show that the sum of the first three odd natural numbers, that would be 1 plus 3 plus 5, those are the first three, is equal to n squared, so 3 squared. That's 9. And yes, 1 plus 3 plus 5 is equal to 9. Great, okay. So this seems to be true at first, but we're going to try to show that it's true for every natural number n. And we certainly can't check them all by hand. So this is a good candidate for an induction proof because we're trying to show that something is true for all natural numbers n. This is not a proof technique that you're going to use if you're trying to show some statement is true for all real numbers, because you can't stack up the real numbers and have them knock each other over the way that you can with the natural numbers. Right? So induction proofs are often good for things like this. Prove for all n and n that something is true. All right, now before we actually jump into the proof, I just want to say we're going to have to check or assume that P of k is true, and then prove that it's true for P of k plus 1. So I just want to be clear about what P of k means. It means in this original equation up here, this is your equation of the form Pn, this is your open sentence Pn, replace n with k. So what this is going to look like is 1 plus 3 plus 5 dot 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 all the way up to 2k minus 1. And I'm going to want to show that that's equal to k squared. So I've just replaced my n's with k's here. That's all you're doing with this P of k stuff. But for P of k plus 1, which is what we want to prove within the proof, we're going to need to go ahead and write this entire equation again, replacing every instance of n with a k plus 1. Right, so this is going to look like 1 plus 3 plus 5, all the way up to, the last one would be 2 times k plus 1. Okay, 2 times k plus 1 minus 1. And we need to show that that's equal to, the right-hand side would be k plus 1 squared. All right, so let's come back to this in a minute, right? But this is essentially what we're trying to show. And bear in mind that the only difference between the P of k statement and the P of k plus 1 statement is on the left-hand side, we're going one term further, right? If we were to expand this at the end, essentially this would be 1 plus 3 plus 5, all the way up to 2k plus 2 minus 1, which really is 2k plus 1. Right, so the difference between the left-hand side here in P of k and the left-hand side here P of k plus 1, is we've got one extra odd number over here. All right, so this is going to come in handy as well. So let's try and understand what this proof looks like. So we will prove this with the principle of mathematical induction. We start with the base case. For the base case, remember what we need to show is that P of 1 is true, that this statement is true when you replace n with 1. So P of 1 says essentially exactly what we have up here. 1 is equal to 1 squared. This is true. That's it, right? Base case is done. You just need to show that it's true for the case when n is equal to 1. Now the induction step's a little bit different, right? This is more work. For the induction step, we let k be greater than or equal to 1, and we assume P of k is true. We then need to show that P of k plus 1 is also true. So let's go ahead and do that. Let k be greater than or equal to 1, and assume P of k is true. That means this equation that we wrote right here, we're assuming that this equation is true. So assume 1 plus 3 plus 5 all the way up to 2k minus 1 is equal to k squared. We call this, by the way, let me just make a note here, this is called our induction hypothesis. Right, this is that P of k statement that we're assuming is true. All right, now we must show, right, it's good to let the reader know where we're going here. We must show that P of k plus 1 is also true. That is, we need to show this equation up here, or if you prefer to write it a little bit more simply using this left-hand side, we need to show 1 plus 3 plus 5, right? Almost the same thing on the left-hand side, except we're going up to 2k plus 1 instead of just to 2k minus 1, is equal to the right-hand side, k plus 1 squared. Okay. This is what we know. This is what we need to show. Okay, so you're always going to be using your induction hypothesis to help you prove that P of k plus 1 is true. And hopefully we can see sort of how to do that, because we know for sure that this is correct. And the only difference between the left-hand side here and the left-hand side here is that we have one extra term at the end. Right? If you want a concrete example of that, the only difference between the n equals 2 case and the n equals 3 case is that you have that one extra term, that extra plus 5 at the end. Right, it's the same idea down here, but just abstract with our k's. So what we can do is we can say, by the induction hypothesis, we have that, I'm just going to write that equation one more time, 1 plus 3 plus 5 all the way up to 2k minus 1 is equal to k squared. And I'm trying to show that this equation is true. So I'm going to try to turn this expression into this expression by just adding in that very last term. The thing is, if I add it to the left-hand side, I also have to add it to the right-hand side. Right? I'm just going to put a star next to this because this is what we're trying to show. Right? So I'm going to add 2k plus 1 to both sides of the equation. Right? This is just the induction hypothesis from above with an extra term added to the end, an extra 2k plus 1 added to the end. Now the left-hand side here exactly matches what we have here. So I just need to show that the right-hand side, k squared plus 2k plus 1, is equal to the right-hand side here. And actually, guess what? It falls right out. If I just factor this factors to k, need to multiply to 1 and add up to 2. That's going to be k plus 1 times k plus 1, which is indeed equal to k plus 1 squared. All right, so we used our induction hypothesis. We just added one extra term on each side, and we were able to prove exactly what we're trying to show here. So we can say now, oh, can't really see it, sorry. We can say now that P of k plus 1 is true. Thus, by the principle of mathematical induction, P of n is true for all n in the set of natural numbers. Oof. Here's our first example. It's done. We'll do another example in the next video.